Good. Yes, so the key point of this, we're not going to go into a big discussion, but the key point of this was to get you to think about setting priors as not a subjective process, right? But as a way, maybe a bit imprecise, of formalizing what you know of the scale. It's not, as many would say, what you believe about the phenomenon, but is what you actually know about the phenomenon. And just by thinking through the scale of the measurement, you know a lot. Okay, now what we want to shift to is to actually assessing contrast, right? So we model articulation as a Gaussian, but we really don't care about that, right? We care about seeing whether the vowel articulation is different in infant-directed versus adult-directed speech. So what we do is we create our second formula, right? Articulation F2, to which we assign a Bayesian formula, BF, where articulation is a function of not only the intercept, as before 1, but the intercept and the register, whether it's infant or adult-directed speech, which is another way of saying that articulation is distributed as a normal distribution with a mean and the standard deviation, and the mean is a linear model. Right? Intercept plus beta times register. That's the traditional idea, with the idea that then intercept is going to be your estimate of articulation in whatever register is the baseline. Since they're called ADS and IDS, it's probably going to be ADS because R likes to put them in alphabetical order. And the beta, or B, is going to be the IDS minus the ADS, right? The difference or contrast between the two. This is, basic linear model, but please ask questions if this is not clear, because it's what we're going to rely on. At this point, what we did is we added a new parameter, right? We added B. We have sigma as before, we have intercept as before, but we also have B. Register is not a parameter because it's a variable. We tell the model whether the specific data point belongs to the ADS or IDS register. So it's not something we need to estimate. It's a predictor. Again, we don't want to be fancy or too clever, so we use the get prior to get which parameter should be assigned a prior, and we get the intercept, right? The mean expected value of articulation where register is baseline or 0. Then we have beta, which is the mean expected difference between register equal 1 and register equal 0. That is IDS minus ADS. And then we have sigma. That is, if we already know the intercept and beta, what is the expected average error in predicting a data point? And this formulation of the linear model is basically indistinguishable from a t-test, where you're comparing two vectors of numbers. But again, we don't really need to worry about which kind of test it is, because we just build the kind of analysis that we want, and we don't worry about how it's called. Okay, looking at this, right, we get that mu, or mean, is defined as that specific equation, which has 2 parameters, right? Now we have 3 parameters. It's just another way of saying what we said before. We set priors on the intercept and on the beta. And again, they're going to be 2 distributions. And if we choose normal, as we will, each of those distributions has a mean and a standard deviation, a mu and a sigma. And the sigma of the initial distribution also has the usual prior, right? So we set the priors, we have the intercept, we keep it as before for now. We have no reasons to keep changing it, right? The distribution of the articulation during adult-directed speech is supposed to follow the scale, since we scaled it, right? We have sigma, that's exactly like before. Again, we might be overestimating a bit the error because we hope that by knowing register, we can reduce the error in our ability to explain the data. But it's a good starting point to say we should expect to do errors like the basic model of the mean. And then we have the beta, right? And with the beta or B, we need, again, to think about what we know. We said that since we scale the data, right, the beta is going to be on the scale of Cohen's-d. And that already tells us something about the range of plausible effect sizes that we could expect. I don't know, what's the kind of effect sizes that you expect in your research when you measure it in Cohen's-d? Right. So, for instance, in social psychology, the average effect size, according to a meta-analysis, is something like 0.2 something. In cognitive neuropsychology or cognitive neuroscience, I actually have no idea, but working on interactions, I'm very happy when I get effect size that's about 0.2, 0.3. So what we could say without knowing much more is that maybe a plausible range for not being too restrictive is something between minus 0.6 and 0.6. Right? That's the kind of effect sizes that I would expect. Does that make sense? And that means that we say that the prior is a normal distribution with the mean of 0, right? We're still conservative, right? We want the data to persuade us that there is an effect, so we center it at 0. And we give it a standard deviation of 0.3 because that says that the model should easily push the posterior, given the data, all the way to minus 0.6 and 0.6. And we think that those like effect sizes beyond that should be supported by exceptional evidence. Is these specific 0.3, right, something that we should put all our money on? Again, no, right? This is a reasonable starting point. We're going to check the model again and again to make sure of the implications of this choice. All right, so here is how we write it. It's just articulation P2 because it's the prior for the second model. And I think I should mention that PowerPoint makes the P's big, but big caps, but in the code they should be small. So here is how it looks like. Right, and here is how we build the model. Again, we start with checking the priors. We say we want the formula for the second model, articulation F2. We want the data. We want family Gaussian. We want the second prior, and we want only to sample the prior. We run the simulations from the model that only samples from the prior. This was how it was before in model 1. And here is how it is with model 2. It's very comparable. It's in the same order of magnitude, so it's good. If you really squint, you can see that the range is slightly broader. And that's because we added an additional parameter so that things can go more extreme in both directions, right? It's not just the intercept as before, but it's the intercept plus the beta. Okay. I see no particular problems here. So we go on and we fit them up. Again, the only thing we change is really the sample prior. We don't say it's only, we say it's true. We do the PP check. What you see is what we had before, right? The prior predictive check. And now we add the posterior predictive check. And again, quite unremarkable, nothing to write home about, but it tells us that the model can hone in pretty nicely on the actual data. The shape is roughly similar, right? There's perhaps a few bumps here and there in the actual data, but that's okay, right? We don't want to overfit to our data. We know that the measurement is noisy, right? So we want just a general shape to be captured. We don't want to capture every little bump, unless we have theoretical reasons to think that they are important. We can do a second predictive check using the functions of the model, so of the BRMS package. So this is using the function called conditional effects, which overlays the population level estimates for ADS and IDS. That is the mean expected articulation for ADS and the mean expected articulation for IDS. And those are the dots with the dot plots with the arrow bars and the actual data points. Right, so we can see how well it's capturing the data and if there is any obvious bias. Of course, we should expect the real data to be broader because this is just the mean, like the mean, the expected average across participants. But as far as I can see, given the limited sample size, there are no obvious biases in terms of capturing or under predicting one or the other, right? I don't know if you see something else. One thing that I see is that one of the two conditions is broader, right? Has a broader variance, or at least has a really big outlier, if you want to talk in terms of outliers, meaning that one of the participants has a really highly articulated IDS speech. And if these were, the traditional statistical framework, we might start wondering whether we should do another test, right? But I have a slide in a bit that will show you how you can incorporate these knowledge, which of course, if you work in psychiatry, is very common, that your target population tends to have a broader variance than the controls into the model without having to change text. But for now, we just assess that there doesn't seem to be any obvious huge bias, right? The spread, at least to me, looks like what we should expect, given that it's a limited sample size. We do the prior posterior update checks. The intercept and the sigma are just like before, but something is going on with the beta, right? The middle plot. Anybody wants to say something about that?
Yeah, so it looks like the mu of the posterior is quite shifted from the mu of the prior.
Yeah, so we see that the posterior has learned something, that the model has learned something from the data, right? It's not completely determined by the prior. Look at the relative height of the two, right? You can see that it has become a bit more confident, but not excessively so compared to the other prior posterior update checks. Right, so what we're seeing is that the prior is constraining the inference a bit, right? And one could say, well, this is a problem, right? Let's go back and make the prior broader because we really want to learn a lot from the data. In this specific case, my stance would be, no, actually, this is good. Right? We are regularizing the inference. We are reducing the potential overfitting to the data. We are making the data work a bit harder to persuade us that there is an effect, especially given that the claim that Danish hypoarticulates infant-directed speech is controversial and surprising. Right? Every other language except maybe Cantonese does hyperarticulate. Why should Danish be different? So by being a bit skeptical in the prior, we make the data work a bit harder. If anything, we underestimate the effect, but we are sure that it's really driven by the data, right? That the data are really pointing in that direction. And that's where I'm saying that this wouldn't pass the Gelman criterion, that the standard deviation of the posterior should be 1/10 of the prior, but it still makes sense from my perspective to use it. From the perspective, well, shouldn't say from my perspective, but from the motivated perspective of the analysis that we're setting up. Again, we might wonder, how far would it go if we were to relax the prior? And we're going to check that in a bit. So what we see if we accept these priors is that the difference is estimated as minus 0.36 with a standard error of 0.21, right? So that's a small to medium effect size. And that estimate would be fine by me, but sometimes we want to explicitly test an hypothesis, right? To assess in a Bayesian framework, how many of the posterior samples are actually compatible with a given hypothesis. You can see that we have a distribution of the posterior that crosses 0, right? And we want to know what a percentage of that distribution of the probability mass actually crosses 0, or actually is negative, or actually is positive, according to the hypothesis that we're testing, right? And indeed, given the previous literature, there are 3 hypotheses that we can test, right? The meta-analysis says that IDS should be hyperarticulated. So we could test the hypothesis that the register effect is above 0. And there we would count the percentage of samples that are above 0 in that orange distribution. How much evidence there is for that. We can see already eyeballing that's going to be pretty small, right? There's very little evidence that IDS is hyperarticulated in Danish, given these data set. The second hypothesis is that one previous Danish study says that IDS is the same as ADS. There is no difference, right? Here we can test the evidence in favor of the null hypothesis, if you want. And again, there's the handy formula syntax from the RMS. Or we could follow Christina's thesis and say, actually, there is a previous study that says the Danish IDS is hyperarticulated. That's the hypothesis we want to test. And it's as easy as changing the sign or the direction of the minor and major, right? And by the way, 0 has no spatial status in Bayesian statistics. So you could say, for instance, the least meaningful effect size would be 0.1. So you could say, you could test the hypothesis that register is above 0.1 or below minus 0.1, right? So there's no reason to stick to 0. I should note that a lot of the hypothesis testing in the Bayesian literature recently has been co-opted by the Bayes factor coalition, right? Bayes factor is a legitimate way of running things. I have some very nerdy problems with that, namely that it really depends on the prior that you choose. So that you can make a Bayes factor change direction of evidence just by changing the shape of the prior, not even where you're putting the evidence. And I like these way that I'm telling you, I test hypothesis, meaning just by counting how many of the samples are compatible with the hypothesis versus the ones that are incompatible with the hypothesis, because it can use any priors. It doesn't depend on a specific class of priors. And I feel it's a bit more transparent, right? It's a bit more directly connected with the way we're setting up the model. I leave the 3 hypothesis testing as an exercise when we do the hands-on, but we can check very briefly the one in terms of hypoarticulation, just so you know how to read that. Right? We test how many of the samples are compatible with the hypothesis that Danish people are actually making it harder for their children to learn. And this is the outcome of the code. You get that the estimate is minus 0.36, as we've seen before. The estimated error or standard error is 0.21. And the confidence intervals are between 0.7, minus 0.7 and minus 0.02. Let's keep to the very last point. The posterior probability, that is the number or the percentage of the posterior samples, the percentage of the probability mass of the distribution that is compatible with the hypothesis, is 96.96, that is 96%. For every 100 posterior samples, 96 are below 0, and only 4 are equal or major than 0. And the evidence ratio, that's simply 0.96 divided 0.04, right? Divided the rest of the samples, is 22.05. And there's 22 times more evidence compatible with hypoarticulation than there is that is incompatible. Right? Is this good enough? Well, again, it depends on how important the problem is, right? If you're testing some intervention for COVID that has potential side effects, you want to be really sure. If you're trying to discuss whether there is a possibility that one language across many has hypoarticulation, then 22 is good enough to start the discussion. If you really want to think in frequentist terms and p-values, right? I shouldn't say this, and I'm being recorded, but Paul Buchner, who has developed the VRMS package, also has the star, which I cut here from the picture. That means if the posterior probability is above 0.95, then there is a star, which is equivalent to the use of the p-value, right? There's only a 5% probability or less that given the data and the model, that the hypotheses that are alternative to ours are true. Or given the data and the model, there's more than 95% probability that the hypothesis that we test is true. And given the data and the model is very important, right? If we trust the data that is representative of the population, if we set up the model right, blah, blah, blah. But at least it's in our hands, while in frequentist statistic, it would be if you were to repeat the experiment an infinite amount of times, right? There is only a 5% or smaller chance that you would get results like these or more extreme. And we have no control about repeating the experiment an infinite amount of times, while we have control about our data and our model. Good. Robustness checks. We had that issue with the beta, right? That keeps gnawing at our minds. It keeps eating us away. Are we really done the right thing by saying that the beta should have a prior centered at 0 and with a standard deviation of 0.3? And the point is, you don't need to keep spending your nights awake thinking about that, because you can get your computer to run through the night and test what are the implications of choosing a standard deviation so narrow, right? So we keep the mu or mean at 0 because we still want to say that as a baseline, we don't really know whether it's going to be hypo or hyper articulating, whether the effect size is going to be negative or positive, right? We have previous evidence for both, and we want the data to work. But we can vary the standard deviation systematically from 0.1 all the way up to 1.5. and see how the posterior estimate changes. Right, and we can see that where we are at 0.3 is the third, right? We are not in a stable region, right? We are pulling the effect towards 0. If we were, I don't know, from 0.7 and above, we would enter a roughly stable region where the effect size doesn't change if we change the prior of a little, right? If we move the prior a bit on the right or on the left, the estimate is roughly the same. And this is something that can be reported, right? I would report, or Chris, when he'll finish that paper, will report that the hyperarticulation, as estimated given our conservative prior, is 0.36. But if we were to be less conservative, see robustness plot figure S1, and there is a region of stability that says that it's about 0.6 something that holds between these and that prior. But we choose to keep the 0.36 because we want to be skeptical. It's an exceptional claim that Danish is different from the other languages. Some people prefer to go to the region of stability, right? And that's also very legitimate. Just report the robustness check so people can actually see for themselves the effect of your prior choice. Does that make sense? Good. So before we close the lecture part for today, I mentioned before that we might worry about heteroscedasticity. What if the variance is not the same between the two groups, which is a common concern in psychiatry, right? Or even when you have whatever sort of manipulation in your experiment, the manipulation might have broader effects than your baseline condition. And indeed, if we just plot the data, we can see that the IDS has a broader range, has a bigger variance. Does that make sense? But we don't need to change the test, right? The only thing that we need to do is to tell the model that it could expect a different level of sigma, a different level of predicted error, average predicted error, if we only know the intercept and register. What we do is we open up sigma. We say that also sigma is a function of register. And here I give you the formula. Articulation tilde 1 plus register, sigma tilde 1 plus register. That's it. But we allow the model to estimate different sigmas, different average predicted errors for the two registers. This is technical terms called a location scale model. It's becoming very popular in personalized medicine or individual time, what's called when you record longitudinal data for a bunch of individuals, you might have that each of these individuals has a different variance, and you can condition the sigma on the individual, right? And you can then get prior, check the priors, and do the same thing as before. The procedure doesn't change. You just told the model that it should do things a bit differently.